Hi, everybody. This is the second lecture for Module 5. This one should be for week 5, although it'll kind of have portions that you might also see in week 6. So just know that week 5 and 6 are covering the immune system. I'm going to go ahead and bring us to our PowerPoint, and I'll spend some time at the whiteboard as well. So with this one, we're going to start talking about the true immune system that humans have as hosts. We, by the end of this, should know the 2 divisions of the immune system. You should be able to list the 3 different types of barrier defenses that the body has and be able to give an example of each type of barrier. Also know or understand the process of phagocytosis. Know the cytokines that play a role in fighting viral infections, and we'll talk about 2 specific ones that we think of, especially with viruses, and then also be able to describe the role of inflammation and fever in helping you fight off an infection. So with that, I'd like to talk about the immune system. So when we think about the immune system, we have a response that is a physiological process that coordinates all of our immune system basically to eliminate an antigen. And an antigen is just a vocabulary word that means something that is going to get our immune system to try to get rid of it. So anything that would be foreign to our body, we would imagine would be considered an antigen. So a virus, especially like the spike proteins or the protein capsid, would be an antigen that our immune system would want to get rid of. And our immune system includes 2 key branches. This particular lecture, I'm going to be talking about the innate immunity. And then in 5.3, I'll talk about the adaptive immunity. It is important, though, to remember that the common feature that both of these 2 branches have is they have the same goals. Number 1, they want to recognize diverse pathogens. So regardless of if it's a virus, a bacteria, some sort of parasitic worm, we want to be able to recognize that. Number 2, to eliminate that identified invaders. And then the number 3 is to be able to tell the difference between self-antigens, because we may not think of our own cells as having antigens, but we do have antigens that are basically are uniform for the body. And I think I talked about that as the glycocalyx, that we can recognize self versus a foreign antigen. And we need to be able to do that, or otherwise our immune system would react to our own cells. So with that, I want to go to the whiteboard and talk a little bit about kind of how we look at this as an overview. And for me, this is kind of the best way to describe this, and we'll come back to this over the next couple of lectures. So if I'm thinking about the immune response, I can break that down, I just said, into 2 main branches. And so the 2 main branches, and I'm going to kind of do this because we're not going to get to one of them until the next lecture. We have our adaptive immunity that we will look at in the next lecture. So I'll put that kind of over here. And then the one that we're going to be looking at today is what we call the innate immunity. And you want to think about this as something that you are born with. You are born with your innate immunity, and it's ready to go from day 1. And we can divide these into kind of 3 lines of defense, basically meaning that as a virus comes into your body, we hope our first line of defense stops it. If it doesn't, we have our second line of defense that's ready to take over. And ultimately, we have our third line if that's needed as well. So with the innate immunity, the first thing we have is what I would call our first line of defense. Okay, and our first line of defense would be what we call barrier defenses. And we'll talk about this in the start of the lecture today, but you can think about this about physical properties of the human body that prevent microorganisms or infectious agents from getting in. So maybe you can think about the tears in your eyes flushing things away. Maybe we can think about the fact that we have eyelashes that keep things from getting into our eyes. Things like that are going to be what we think of with barrier defenses. So barrier defenses, their whole goal is to keep a pathogen from getting into the body. So I'm going to put prevent entry, right? But as we probably know, many of these things still gain entry, and that's where hopefully our second line of defense will come into play. And the second line actually gets divided into two parts. We have the first part, which we will call it cellular, meaning that there's cells that play a big role in this. And the big thing that we see here is phagocytosis, which we'll get into. But this is basically that we have cells in our body that act as scouts, that basically are throughout our body looking for anything that might be foreign, that then they can attack and basically chew up and destroy. That's the cellular portion. The other portion we have of our second line is what we would call molecular. And this usually has to do with chemicals that are circulating in the body that can actually help us with our immunity. And so I'm going to actually number a few of these. The first is what we call cytokines, which we'll get into in a minute. And cytokines are chemicals that our immune system uses to basically help protect us. And there's a couple that we would see in this. We have interferon, and then we have something called the complement pathway. We'll talk about both of these today. And then the second and third thing that we see as kind of molecular would be the idea of inflammation. Inflammation can actually help us fight off an infection or repair damaged tissue. And the third that we hinted at in the last lecture is fever. So the ability of the body to increase the temperature. So this is the whole thing that we're going to go through today, but it's always nice to kind of look at this wrapped up kind of in a concept map. So again, starting with that immune response at top, I then have the innate immunity, and this is going to be lecture 5.2. And with adaptive, we're going to get into that in lecture 5.3. So my hope today is to talk about the first line of defense and then the second line of defense. But hopefully this helps you kind of get it organized, and it's likely that this would be a good thing to come back to look at how the immune system is organized. And I do want to mention that although these look like they're separate lines of defense, and I will put that this is the third line of defense, do keep in mind that these overlap with each other. So just because we have something going to the second line of defense, it doesn't mean that our barrier defenses are no longer working. Or if we go to the third line, that we don't have fever and inflammation. It's just easier to compartmentalize these. So if we go back to our slideshow, as I said, they have the three different lines of defense in these two branches have common features. They both have the same goal. So let's go ahead and get started. As I said, that the two parts under the innate immune system would be our barrier defenses and then our cellular and molecular defenses. One thing that I want you to keep in mind is that the innate immune system is what is considered non-specific, meaning that it doesn't matter if it's the measles or the common cold or hepatitis that you're exposed to, your immune system will react to it, the innate immune system, as though they're all the same. And so the immune cells and enzymes that are involved in this, in the innate portion, don't actually have any memory from prior encounters with it, and so therefore treat everything the same just as a foreign invader. This will be different when we get to the adaptive immunity or the third line of defense. So the key components or the key thoughts on innate immune system are that it's non-specific and there's no memory. So whether I'm exposed to the common cold tomorrow or I'm exposed to measles, my innate immunity looks at them both as foreign and wants to get rid of them, nothing more than that. So as I said, the first line of defense is what we call our barrier defenses. And the first line of defense fall into three different ways that we can think of these barrier defenses. We can have what is called mechanical, chemical, or physical. And again, all of these, their goal is to prevent pathogen entry. So let's start with the mechanical. That's going to be anything over here in green. And so you can think of this as any way that your body normally flushes, rinses, or traps microbes or anything that might be trying to enter it. So for example, your eyes water when you get something in your eye, and that's to flush anything out. In addition, in our respiratory tract, we talked about the fact that there are cilia that line the respiratory tract. that use movement to sweep those particles back up out of the respiratory tract so that they can't get into the lungs. So this is what we would consider mechanical. You could also think about urine flushing through the urinary tract system that flushes out any pathogens. The second one is chemical, meaning that there are chemicals in certain parts of our body that actually play a role in defending our body from an infection. And so chemical are molecules that directly attack any kind of microbe or make an environment so unwelcoming that the pathogen doesn't want to stay. So one of the things that we have is we have this enzyme that is found in our tears, our mucus, saliva, and even breast milk, which actually has the ability to kill bacteria. Now, this won't kill viruses, but you still want to think about this as part of your immune system. The second part to chemical could be something like the stomach. Our stomach has a very acidic environment, and very few pathogens can survive or be able to replicate in our stomach because of that acidity. And then we also have throughout the body what are called antimicrobial peptides. So anti, the A is for anti, M for microbial, and P for peptides. And these are found throughout our body, even in our blood, that can destroy pathogens. And they're chemicals that basically attack foreign invaders. And then the last one that I want to talk about is the physical barriers. So the best known or the most probably protective of our physical barriers would be things like our skin that are a structural blockage for anything to get into the body. You can also think about your eyelashes, even hairs in your nose can block things from getting further into the respiratory tract. So that would be our first line of defense. So if we were to go to our whiteboard, that would have been this very first part. Let's see if I can get a color. This was what we were talking about here, was our first line of defense, right? And we talked about the fact that you could have mechanical, you could have chemical, and you could have physical barriers. Okay, and that kind of takes care of our first line of defense. And again, its whole job is to stop entry, right? Anything from entering the body. So going back to our slides, that brings us then to our second line of defense. And the first thing that I had under that was the fact that there was a cellular portion. And this really is talking about phagocytosis. As I said, there are many different cells that act as scouts within your body that basically are looking for a foreign invader. You can think of them as kind of the scouts for an army, if you will, of looking for anything that looks like it could cause trouble. The main ones that we think of that do this phagocytosis are cells. The cells that we can think of are neutrophils, monocytes that mature into macrophages, and dendritic cells. These are all white blood cells that their whole job is to do phagocytosis. And phagocytosis just means that they have the ability to attack and destroy foreign molecules. In addition, not only will they kill or destroy a virus if it comes in or a bacteria, but they can also take parts of it and actually present it to the third line of defense so that the third line of defense goes after it as well. So basically they can do like a head on a stick, if you will, and I'll draw this for you of the way that I think of phagocytosis. So when we go to the whiteboard, if we do phagocytosis down here, you can kind of think of one of these phagocytes. So that would have been a neutrophil or a monocyte or a macrophage or a dendritic cell. And maybe we had this little virus over here, okay? So I'm going to put this as a virus. And this is a phagocyte. And what happens is when this comes in contact with a virus is that it will actually basically eat this up. It will take this and bring it in. And at this point, we call this, put that virus in there. This is actually called a phagosome at this point. And hopefully you guys remember, we talked about something called lysosome. You don't remember what that is, you might want to go back and look in your notes, but lysosomes basically have these hydrolytic enzymes are very destructive enzymes. And what can happen is that these two can merge together. And we get something with that little virus guy in there. We get something that we would call a phagolysosome. And what happens here is that all of those enzymes that were in there, those green kind of dots, basically shred this all up and kill that virus or deactivate this virus. And that's great because we don't want those viruses going around. But the other thing that this phagocyte can do is that this phagocyte can actually present on a protein outside of it a little bit of that virus. So in this case, it presents an antigen. And this would be to cells in the adaptive immunity. Adaptive immune system. So when we get to the third line of defense next week, you'll be able to see where this would come into play. So not only does it kill it, but it actually will then notify basically the adaptive immunity that, hey, this intruder came in and you guys should really be looking for this little black, whatever this antigen is, and go out and kill them when you see them. So that covers phagocytosis, which is our cellular under our second line. And I think I have a short little video of this too. So we'll go back. I have a video, actually, I think I already have it up in another window. And this will give you a chance to see that. Let's see if it's going to let me do that. Well, let's see. Here we go. I'm going to go ahead and play this. And this is showing phagocytosis, what it looks like. In this case, it's showing bacteria that are getting eaten up, but the same would be true for viruses. So hopefully that was helpful in kind of looking at what that looks like when we have phagocytosis. And you're welcome to go back and watch that if you want. Even though they were showing it of a bacteria or bacteria that were being eaten up, this is true for viruses as well. So that takes us to then the last part of our second line of defense, which is going to be our molecular portion of this. And so we're going to talk about both cytokines, and then we're going to talk about inflammation and fever. So in the molecular second line of defenses, what you want to think about is those leukocytes or white blood cells. When they are called into action, for example, to do phagocytosis, they can often release molecules into the local environment. And they release what are called cytokines, which are these chemicals that allow immune cells to communicate with each other. And basically what this does is it allows the immune system to get other cells involved and to coordinate that action in getting rid of this foreign invader. Most cells in our body are capable of making and releasing at least one type of cytokine, but we know that especially the immune cells can make many of these and coordinate that immune system. So the first one that I want to talk about is the one that plays the biggest role really with viruses, and that's what are called interferons. And interferons are when a virus-infected cell basically sends off a chemical signal to warn neighboring cells around it that are not yet infected. And basically, they tell those other cells to mount a defense. So I like to think about this as if I was in a neighborhood and my house was broken into, and I knew that the people were going to go to my neighbors' houses, what I could do is I could actually warn them. Maybe I'd call them or just let them know, and they would be able to make sure that their doors and windows are locked. I might already have been robbed, but I'm protecting those around me. So in this case, what you can see here is it's showing a virus that gets into a particular cell. So a host cell, it gets in, right? It unlocks its way in and it gets in. And this host cell realizes, oh no, I've been infected by a virus, which likely I'm not going to survive. But what I can do is warn my neighbors. So it can signal uninfected cells next to it to basically slow down their protein synthesis, because remember, viruses depend on that, and that would stop virus replication. They can also send messages that will cause other infected cells nearby to basically go through what is called apoptosis or cell death. So in the bottom here, this bottom cell is another infected cell, and it's basically telling it you need to get rid of yourself so you don't spread the virus more. And then it can also send interferon to other white blood cells, which will activate those white blood cells to come to this area and help fight off this infection. So interferons play a very large role. They don't stop the infection in that cell that's already been infected, but they help it to save those around it. So that's a really cool thing about interferon. And I always think of it as interfering with the spread of the virus. The second thing that I want you guys to know about the molecular portion is, and the cytokines, is something called the complement cascade. And you really want to think about this. This is a pretty complex system or pathway. And so I don't want you guys to get caught up in that. I just want to kind of do an overview of talking about the fact that there are these proteins that are basically circulating in the blood that are inactive. But when they are activated, what they can do is they can help the immune defenses. And so there's three possible things that can happen if this complement system is activated. And often it's activated by cytokines that a phagocyte might have released. So the three things that it can do is that one of them is it can do what is called opsonization. And this is where some of these proteins will actually attach themselves to the virus or the bacteria so that it makes them more noticeable to other phagocytic cells. So it might basically flag some of these viruses that have invaded the host so that phagocytes can see them more clearly. The second thing it can do is something called a membrane attack complex. And basically this is a group of these complement proteins coming together to form a complex that can actually break down a cell. And maybe they do this to an infected cell to get it so that it doesn't survive and help the virus replicate. And then the third thing that the complement cascade can do is increase that inflammation in that area. And we're going to get into why that might be helpful in the next part of this. So hopefully this gives you some idea. Again, if we go back to where we were on the whiteboard, some of the things that we've talked about then, try to make sure I've kind of got this, but we talked about the first line barrier defenses, right? The mechanical, chemical, and physical. We went to the second line where we talked about the cellular, and that was really looking at phagocytosis. And that was showing, right, our phagocyte that was actually going to break it down. And then we've just done the molecular, the cytokines, where we've talked about interferon and complement pathway. The last two things I want to talk about then are inflammation and fever. So as we think about it, inflammation and fever actually have this key protective ability in the human body. So when a threat is detected, what we typically see is that the tissue cells and local white blood cells will release these chemical mediators or these cytokines, right? And what happens then is that attracts the cellular defense to converge on the scene. Remember, the cellular defenses are those phagocytic cells. When that happens, we have cytokines and complement proteins and all this pro-inflammatory factors that coordinate to help out. And so what we often see then is that inflammation gets triggered and sometimes fever. So what is inflammation and why is it a benefit in an infection? So inflammation is a really important part of the immune defense, and primarily its role is to help with healing. It happens when tissues get damaged in a particular area to help those tissues heal. So remember, we talked about in last week's lectures the fact that viruses can damage cells and even kill cells, and that damage, then we want to make sure that we can heal that. And so the three main goals of inflammation are, number one, they recruit more immune defenses to the injured tissue to make sure that the infection is taken care of. That inflammation also causes it to limit the ability of that infectious agent to spread further in the body, because with inflammation, what we see is it gets concentrated in that area. And then lastly, it will deliver oxygen and nutrients and other chemical factors that will help that tissue recover. So as we think about that, right, that has the same thing at the top. But what I want you to think about is that there are some cardinal signs of inflammation that we can think about. And I'll explain what each of those, why we get those. So the first is redness. You've probably noticed that when you have inflammation, there's redness, or what we would call rubor. And this is because we have dilation of the blood vessels that bring more blood to that area. And so that makes it look red, especially if you have fair skin. That's where we tend to see that. It also causes pain, which we refer to as dolor. And often that's because with inflammation, all this influx of fluids to the area, it puts pressure on our nerve endings that we perceive as pain. You can have localized heat. It's not fever, but it's just localized to that area. And that's often caused, again, because we have blood rushing to the area. Blood is coming from the core of the body, often warming that area when it's there. And then swelling. Because so much fluid is coming to that area, we tend to see the tissues swell there with the fluid in there, and we refer to that as tumor. Lastly, if we have really bad inflammation, so quite inflamed, we could have loss of function for a short period of time, so temporarily, because it's so swollen that we don't have range of motion. So inflammation falls into three phases, and I expect that you guys should know the three different phases. And we'll go through just kind of briefly talking about these. So the first thing is that we have these vascular changes. And what that means is that in that area, what we expect to see is the blood vessels will actually get larger and the walls of them will get thinner. And this allows more blood flow to get there, but also will then allow those white blood cells to go out of the blood vessels and into the tissue to start taking care of the issue, the infection or the injury. The second thing that we should see is what is called leukocyte recruitment. So the recruitment of white blood cells. This is cytokines that get released that bring in more neutrophils and monocytes and different phagocytes to come in and help clean up the mess, right? Take care of the infection and clean it up. And then the third step is what we call resolution. And at this point, once the actual danger has been taken care of, so the virus has been deactivated and chewed up by all these phagocytes, we expect to see inflammation signals start to decrease and that tissue repair and going back to being healthy. Now, this could take hours or days, and sometimes it can even take a week or two to get that full recovery. But inflammation really plays a role in that tissue repair. The last part of this chapter or this lecture is on fever, and I hinted at this in the last lecture. But fever is another way that our second line of defense can protect us. And so fever, which can be called pyrexia, which is just an elevated temperature or an elevated systemic body temperature, is usually caused by pyrogens, so fever-inducing agents. Often that's cytokines that are released, things like interferon, but sometimes viruses and bacteria have the ability to produce pyrogens too that can increase that temperature. So we often think about this then that it's a signal received by our hypothalamus in the brain, which is what sets our thermostat at our normal temperature of 37 degrees. And it will actually increase that to help our body fight off the infection. So what is it that a fever does for us? There's a couple of different things that it does. First, it enhances the antiviral effects of interferons. So those interferons that were warning other cells or getting rid of infected cells, it increases their effects. So that's a good thing if we have a viral infection. It also increases phagocyte efficiency. So the ability of those phagocytic cells to basically chew up any invaders, it increases that. And lastly, it enhances the leukocyte production, meaning that all those white blood cells that we need in an infection will be increased. The production of them will be increased. So fever plays a major role in helping us to get better or to fight off an infection. And so with that, we often think of low-grade fevers, so those that would be between 37.5 to 38.3 Celsius, and if you're looking at Fahrenheit, that would be up to 101, are considered protective. So most healthcare providers would actually argue that with a fever that's up to about 101, it's likely that allowing it to run its course will actually help you fight off the infection as long as you are healthy. So if you're a healthy individual and you have a low-grade fever, we generally would say don't take something to lower it because that's actually aiding your immune system. As the fever goes up, though, we can see that it can become more problematic. So any fever that reaches 40.5, that would be 105 Fahrenheit, and does not decrease when you're giving yourself something that should be bringing it down. So if you're taking Tylenol or Advil or aspirin and it's not bringing it down, we would then think of that as life-threatening, and it would be an emergency to get in to see somebody. And then lastly, there can be something like too high of a fever and a body temperature above 43 degrees Celsius, or that would be over 109 Fahrenheit, is considered fatal. So if we see that you have a fever over 105, that's when medical intervention is really needed. But in general, those low grade to moderate, we think of that as actually helping your body fight off an infection. So with that, we've covered the innate immunity. I'm going to pause here and let you look these over and answer these. Hopefully you're writing down the answers before checking back with me, and then I will go ahead and give the answers to these. So the first question is, what is the difference between innate and specific immunities? So I said that the innate does not have a memory and is non-specific, meaning that it doesn't matter if it's chickenpox or it's the common cold, your innate immunity responds the same way to everything. We haven't really talked about it yet, but specific immunities, or the adaptive immunity, actually is specific for the disease that it's being presented with. And it's the one that means that if you had measles as a child or you were vaccinated, you now have immunity to that, so you can't get it again. And that's because it is what we would call specific. It can recognize a specific pathogen, and it has a memory. So I always joke that it holds a grudge. So your specific or adaptive immunity actually is can have a memory of previous encounters with a pathogen. The second question is asking, name one mechanical barrier. I think of the cilia in our respiratory tract that actually move dust and particles up the respiratory tract and out of it so that things can't get to the lungs. What are the main phagocytic cells? That would be the neutrophils, monocytes and macrophages, and dendritic cells. What are cytokines? These are chemicals that coordinate and activate the immune system and allow communication amongst the different cells in the immune system. What are the benefits of inflammation? Inflammation can limit the area of the infection and aid in repair of damaged or dead tissue. What are the benefits of fever? The benefits of fever are often that it enhances interferon, it increases the production of white blood cells and phagocytes. And did I have anything else on that? I can't remember. Go back one. Increasing the number of white blood cells that are produced as well. So hopefully this was helpful. I know it's a lot of information, but hopefully spreading this over 2 weeks, it'll feel manageable. Please don't hesitate to reach out if you have any questions for me. I'll talk to you in the next lecture. Thanks.